The most distant human-made object, NASA's Voyager 1 spacecraft, is in interstellar space.
What is the furthest human-made object in the universe? The answer is definitely the Voyager spacecraft, which is presently far away deep in space. However, what is astonishing to scientists is how the spacecraft recently came in contact with a strange force. What is this force all about, and will its influence reach us on Earth? Stay tuned as we bring you all the details about how Voyager 1 makes contact with an unknown force deep in the universe. When NASA launched the Voyager mission more than 40 years ago, none of the engineers or scientists imagined it would last till today. But the twin spacecraft are still alive and sending back signals despite being so far away. NASA launched the twin spacecraft Voyager 1 and Voyager 2 from Cape Canaveral, Florida in separate months in the summer of 1977. The Voyagers were originally intended to conduct close-up studies of Jupiter and Saturn, as well as Saturn's rings and the two planets' larger moons. The spacecraft were designed to last 5 years in order to complete their two-planet mission. However, as the mission progressed and all of its objectives were met, additional flybys of the two outermost giant planets, Uranus and Neptune, proved feasible and irresistible to mission scientists and engineers at the Jet Propulsion Laboratory in Pasadena, California. Remote control reprogramming was used to endow the Voyagers with greater capabilities than they had when they left Earth, as the spacecraft flew across the solar system. Their two-planet mission expanded to 4. Their lifespans ranged from 5 to 12 years or more. Voyager 1 and 2 would eventually explore all of our solar system's giant outer planets, 48 of their moons, and the planet's unique systems of rings and magnetic fields. Even if the Voyager mission had ended with just the Jupiter and Saturn flybys, it would have provided enough data to rewrite astronomy textbooks. However, having doubled their already ambitious itineraries, the Voyagers returned to Earth information that has revolutionized the science of planetary astronomy, helping to resolve key questions while raising intriguing new ones about the origin and evolution of our solar system's planets. The Voyager mission was designed to take advantage of a rare geometric arrangement of the outer planets in the late 1970s and early 1980s, allowing for a 4-planet tour with the least amount of propellant and travel time. This configuration of Jupiter, Saturn, Uranus, and Neptune, which occurs approximately every 175 years, allows a spacecraft on a specific flight path to swing from one planet to the next without the need for large onboard propulsion systems. Each planet's flyby bends the spacecraft's flight path and increases its velocity sufficiently to deliver it to the next destination. The flight time to Neptune was reduced from 30 years to 12 years using this gravity assist technique, which was first demonstrated with NASA's Mariner 10 Venus-Mercury mission in 1973 to 74. And while the 4-planet mission was known to be feasible, it was deemed too expensive to build a spacecraft capable of traveling the distance, carrying the necessary instruments, and lasting long enough to complete such a long mission. As a result, the Voyagers were only funded to conduct intensive flybys of Jupiter and Saturn. More than 10,000 trajectories were considered before settling on the two that would allow close flybys of Jupiter and its large moon Io, as well as Saturn and its large moon Titan. And the flight path chosen for Voyager 2 also preserved the option to continue onto Uranus and Neptune. Voyager 2 was launched first from the NASA Kennedy Space Center in Cape Canaveral, Florida on August 20, 1977, followed by Voyager 1 on a faster, shorter trajectory on September 5, 1977. Both spacecraft were launched into orbit on Titan Centaur expendable rockets. Voyager 1 arrived at Jupiter on March 5, 1979, and Saturn on November 12, 1980. Followed by Voyager 2 arriving at Jupiter on July 9, 1979, and Saturn on August 25, 1981. The trajectory of Voyager 1, designed to send the spacecraft close to the large moon Titan and behind Saturn's rings, bent the spacecraft's path inexorably northward out of the ecliptic plane, the plane in which most planets orbit the Sun. Voyager 2 was programmed to fly by Saturn at a point that would automatically direct the spacecraft toward Uranus. The spacecraft Voyagers 1 and 2 are identical. Each is outfitted with instruments to carry out 10 different experiments. Television cameras, infrared and ultraviolet sensors, magnetometers, plasma detectors, and cosmic ray and charged particle sensors are among these instruments. Furthermore, the spacecraft radio is also used for experiments. Now, the Voyagers are too far away from the Sun to use solar panels, so how do you keep a spacecraft so far away powered for decades? This is where radioisotope thermoelectric generators, or RTGs, come in. These devices, which have also been used on other deep space missions, convert the heat generated by the natural radioactive decay of plutonium into electricity, which is then used to power the spacecraft's instruments, computers, radio, and other systems. The spacecraft are controlled and data is returned via the Deep Space Network (DSN), a global spacecraft tracking system run by JPL on behalf of NASA. DSN antenna complexes are located in the Mojave Desert of California, near Madrid, Spain, and in Tidbin Billa near Canberra, Australia. The closest approach of Voyager 1 to Jupiter occurred on March 5, 1979, and the closest approach of Voyager 2 occurred on July 9, 1979. The first spacecraft approached the planet's cloud tops at a distance of 277,400 kilometers, or 172,368 miles. While Voyager 2 approached at a distance of 650,180 kilometers, or 404,003 miles. Jupiter is the largest planet in the solar system, made up primarily of hydrogen and helium, with trace amounts of methane, ammonia, water vapor, and other compounds, as well as a melted rock and ice core. Jupiter's dynamic weather system is depicted by colorful latitudinal bands, atmospheric clouds, and storms. The massive planet is known to have 16 moons. The planet orbits the Sun once every 11.8 years, and its day lasts 9 hours and 55 minutes. Although astronomers had studied Jupiter through telescopes on Earth for centuries, many of the Voyager findings surprised scientists. The Great Red Spot was revealed to be a complex storm moving anti-clockwise, and throughout the banded clouds there were numerous smaller storms and eddies. And the discovery of active volcanism on Jupiter's satellite Io was by far the most unexpected. It was the first time active volcanoes were discovered on another solar system body. The Voyagers observed the eruption of 9 volcanoes on Io as a group, and there is evidence that other eruptions occurred in the intervals between the Voyager encounters. Volcano plumes reach more than 300 kilometers, or 190 miles above the surface. The Voyager saw material ejected at speeds of up to 1 kilometer per second. The volcanoes on Io are thought to be caused by tidal pumping heating the satellite. Io's orbit is perturbed by Europa and Ganymede, 2 other large satellites nearby, before Jupiter pulls it back into its regular orbit. This tug of war causes tidal bulges of up to 100 meters, or 330 feet on Io's surface, compared to typical tidal bulges of just 1 meter or 3 feet on Earth. Part of the discoveries made possible by the Voyager mission is that volcanism on Io appears to have an impact on the entire Jupiter system, as it is the primary source of matter in Jupiter's magnetosphere, that is, the region of space surrounding the planet influenced by the Jovian magnetic field. Sulfur, oxygen, and sodium were detected as far away as the outer edge of the magnetosphere, millions of miles from the planet itself, apparently emitted by Io's many volcanoes and sputtered off the surface by the impact of high-energy particles. And in Voyager 1's low-resolution photos, Europa showed a large number of intersecting linear features. Scientists initially thought the features were deep cracks caused by crustal rifting or tectonic processes. The closer, high-resolution Voyager 2 photos, on the other hand, perplexed scientists. The features were so devoid of topographic relief that one scientist suggested they might have been painted on with a felt marker. However, Europa could be internally active due to tidal heating at a level 1/10 or less of that of Io. And Europa is thought to have a thin crust of water ice less than 30 kilometers or 18 miles thick, floating on a 50-kilometer or 30-mile deep ocean. And Jupiter's Ganymede is the largest moon in the solar system, with a diameter of 5,276 kilometers, 3,280 miles. It revealed 2 distinct types of terrain, cratered and grooved, implying that Ganymede's entire icy crust has been stressed by global tectonic processes. Callisto has an extremely old, heavily cratered crust with remnant rings of massive impact craters. The largest craters appear to have been erased over geologic time by the flow of the icy crust. The ghost remnants of the massive impact basin show almost no topographic relief, distinguishable only by their light color and the surrounding subdued rings of concentric ridges. And around Jupiter, a faint dusty ring of material was discovered. It is 129,000 kilometers or 80,000 miles from the planet's center and extends inward about 30,000 kilometers or 18,000 miles. Adrastea and Metis, two new small satellites, were discovered orbiting just outside the ring. Thebe, a third new satellite discovered between the orbits of Amalthea and Io, was also discovered. It was found that Jupiter's rings and moons are surrounded by an intense radiation belt of trapped electrons and ions in the planet's magnetic field. The Jovian magnetosphere or magnetic environment consists of these particles and fields and extends 3 to 7 million kilometers towards the Sun and stretches in a windsock shape at least as far as Saturn's orbit, a distance of 750 million kilometers, 460 million miles. The magnetosphere sweeps past Io as it rotates with Jupiter, removing about 1,000 kilograms or 1 ton of material per second. The material condenses into a torus, a donut-shaped cloud of ionized water that glows in the ultraviolet. Some of the torus's heavy ions migrate outward, inflating the Jovian magnetosphere, whereas the more energetic sulfur and oxygen ions fall along the magnetic field into the planet's atmosphere, causing auroras. As it moves through Jupiter's magnetic field, Io generates 400,000 volts across its diameter and generates a 3 million ampere electric current that flows along the magnetic field to the planet's ionosphere. Then came NASA's decision to extend the Voyager mission with what is called the Voyager Interstellar mission, whose purpose is to extend NASA's solar system exploration beyond the neighborhood of the outer planets to the limits of the Sun's sphere of influence and possibly beyond. This extended mission is still characterizing the outer solar system environment and looking for the heliopause boundary, the limits of the Sun's magnetic field and the outward flow of solar wind. NASA's Voyager 1 spacecraft was 11 billion miles or 18 billion kilometers from the Sun on August 25, 2012, and scientists determined that the venerable spacecraft had crossed the boundary between the Sun's influence and the interstellar medium. Voyager is still going and sending back data, so it's still doing groundbreaking science. When it was 122 astronomical units away from the Sun, Voyager 1 became the first human-made object to explore interstellar space, the space between stars in a galaxy. 1 AU equals about 93 million miles or 150 million kilometers, which is the average distance between Earth and the Sun. Because of particle density, scientists are certain that the Voyager probes have crossed from the heliosphere, where the solar wind, a stream of charged particles from the Sun, dominates, into interstellar space. The density was 10 times greater than what obtains in the solar wind at those distances. According to late 2018 readings, Voyager 1 escaped. When Voyager 2 entered interstellar space on November 5, 2018, its instruments detected the same increase in particle density. Now, interstellar space, or the space between stars, is more than just empty space. There's a lot of stuff out there, including hydrogen at 70% and helium at 28%, both of which were created during the Big Bang, which set our universe in motion. The remaining 2% of stuff in interstellar space is heavier gases and dust, which are made inside stars and ejected into space by supernovae. However, the material in interstellar space is extremely dispersed. It is denser in some places than others, but the average density is 1 atom per cubic centimeter. Even the densest regions of interstellar space, when compared to our earthly air, count as a vacuum. Our Sun governs the conditions in our solar system, but beyond that is interstellar space and everything it contains. This space between the stars is known as the interstellar medium by astronomers. But what is the significance of interstellar space? Well, stars are formed in the interstellar medium. We would not exist without it. The universe would be a cloud of boring, cold, lifeless gas if there was no thick and thin spots that condensed into thicker patches that eventually became stars. The thick parts of the interstellar medium are known as molecular clouds, and they are frequently referred to as stellar nurseries or places where stars are born. Because there were no materials in interstellar space other than hydrogen and helium, the first stars did not have planets. But that has changed over the billions of years of our universe's existence. It changed because stars are incorporating increasingly complex elements into their interiors. When the most massive stars die and explode as supernovae, their elements are released into interstellar space. As a result, stars can form with planets, and at least one of the planets we know of, Earth, can support life. Given the contents of interstellar space and the processes by which stars and planets form, it appears highly likely that other planets have life as well. Our local star is the Sun. It is approximately 870,000 miles or 1.4 million kilometers across, or 100 times the diameter of our planet Earth. More than 965,000 Earths would be required to fill the volume of the Sun. Earth is one of our solar system's smaller planets. The solar wind is a stream of charged particles that emanates from the upper layers of the Sun's atmosphere. The Sun and its solar wind create the heliosphere, a kind of cavity that surrounds our entire solar system. The heliosphere is similar to a balloon with our Sun and planets inside. Interstellar space exists beyond the heliosphere. Neptune, the farthest planet in our solar system, is 30 times the distance from the Sun as Earth. The distance between Earth and the Sun is measured in astronomical units, and Neptune is 30 AU away. At about 120 AU, the heliosphere's edge is 4 times as far. The heliosphere is moving through the space of our Milky Way galaxy. As it moves, the side of the heliosphere that faces the center of our galaxy receives more pressure than the side that faces away, causing the heliosphere to stretch out into a teardrop shape. Now, the Voyager probe's passage into interstellar space was straightforward, but the heliopause revealed unexpected properties. Each spacecraft took several months to pass through, during which time they sent back data on plasma density peaks and troughs. The heliopause is the transition zone between the solar wind and the interstellar medium. The solar wind blows a bubble into the interstellar medium known as the heliosphere. The outer edge of this bubble is where the strength of the solar wind is no longer strong enough to push back the interstellar medium. This is what's known as the heliopause, and it's widely regarded as the solar system's outermost boundary. The heliosheath is the region between the termination shock and the heliopause. The termination shock is a boundary in the solar system that marks one of the outer limits of the Sun's influence. It is the point at which the bubble of solar wind particles slows to a speed slower than the speed of sound. When the solar wind particles enter the interstellar medium, they slow down. The solar wind is made of plasma, and as it slows, it undergoes numerous changes. The solar wind plasma is smushed together or compressed like people crammed into a small space. Scientists expected a bleep, but the heliopause isn't like a line or a door. It's much thicker and more complex than expected. But it's also a boundary that allows communication. The incredible discovery that particles enter and exit the heliosphere was made using magnetic field data from Voyager 1 in 2012 and Voyager 2 6 years later. Scientists were perplexed by the data from Voyager 1 and 2 on magnetic fields in the heliopause. Theorists expected the magnetic field from the galaxy to be inclined to the solar magnetic field, so there should have been a change where the magnetic field from the Sun met that from space. However, neither Voyager 1 nor Voyager 2 detected changes in magnetic field direction. There was no change in the angle when Voyager crossed. The magnetic field remained almost solar-like with no rotation. One of the proposed theories about magnetic field flux tubes in the heliopause that connect the solar and interstellar fields. It's almost as if there are these highways for particles to go in and out of the heliosphere, and it's most likely a region where the magnetic field reconnects. The heliopause appears to be a warped heliosphere surface that responds to solar activity, but why is unknown. It also becomes much hotter when compressed, similar to how a bicycle pump heats up in your hand when you vigorously inflate a tire. And furthermore, the solar wind carries some of the Sun's magnetic field outward, which now becomes stronger at the termination shock and twists around. However, we only have 2 direct distance measurements for the termination shock. Voyager 1 and Voyager 2 made these measurements. Voyager 1 is now 40 AU beyond the heliopause, allowing scientists to learn more about the interstellar medium. It turns out the heliosphere has a much greater influence than previously thought. As measured by the Voyager probes, the interstellar medium is agitated and influenced by the Sun. It is so different than expected, and nobody really understands what is going on. According to the data, galactic cosmic rays behave differently depending on whether they are parallel or perpendicular to the magnetic field of the Sun. The data can be linked to coronal mass ejections, CMEs, from the Sun, which cause magnetic field disturbances far out into the interstellar medium. It has compelled scientists to reconsider how cosmic rays can reach Earth. The Voyager spacecraft, the silent ambassadors, will eventually go silent as they enter the pristine interstellar medium, according to scientists. As the Sun's influence fades and turbulence decreases, the probes will most likely detect a matter mix from other stars. The spacecraft, however, are incapable of detecting the influence of the next star alone. In 40,000 years, Voyager 1 will pass close to a star called AC plus 793888 in the Camelopardalis constellation, while Voyager 2 will pass close to a star called Ross 248 in the Andromeda constellation. With the two spacecraft nearing the end of their operational lifetimes as their power supplies deplete, mission personnel estimates that the last time scientists hear from them will be in the 2030s at most. The next spacecraft of interest to scientists studying the heliosphere will be New Horizons, the spacecraft that imaged Pluto in 2015. New Horizons will enter the heliopause around 2030, but its power supply will run out by then. Meanwhile, scientists are considering the Interstellar probe, a decades-long mission to study the heliosphere and expand on the findings of the Voyagers. But let's now go back to 2021, when Voyager 1 sent back a message stating that it had detected a faint, monotonous hum of interstellar gas or plasma. Cornell University astronomer Stella Koch-Ocker led the study and described Voyager 1's discovery in a statement. Because it is in a narrow frequency bandwidth, it is very faint and monotone. The faint, persistent hum of interstellar gas has been detected. Although Voyager 1 is traveling in interstellar space, it is still affected by the solar wind, which is a stream of charged particles from our Sun. This stream from our Sun is no longer the dominant force affecting Voyager 1, but it is mixed in with similar winds from other stars. As Voyager 1 reads its environment, scientists gain a better understanding of how the interstellar medium and solar wind interact, as well as how external forces shape the solar system's heliosphere bubble. The plasma wave system on Voyager 1 has been detecting larger solar eruptions that affect the plasma or ionized gas in interstellar space. A background hum can be heard when the eruptions are quiet. Cornell University team member James Cords described the hum as something much more pleasant than an annoying drone. The interstellar medium is similar to a gentle rain. A solar outburst is analogous to detecting a lightning burst in a thunderstorm and then returning to gentle rain. The low-level hum enabled scientists to study the distribution of interstellar plasma in the space through which Voyager 1 is traveling. That is enormous. We've never had a spacecraft so far away from Earth before, so we couldn't get this kind of direct measurement before. Cornell University team member Shami Chatterjee explained how the hum helps scientists learn more about interstellar plasma. We've never had the opportunity to evaluate it. We now know that measuring interstellar plasma does not require a chance event related to the Sun. Whatever the Sun is doing, Voyager is sending back information. Here's the density I'm swimming through right now, says the craft. And now it's here, now it's here, and now it's here. Voyager is quite far away, but will continue to do so indefinitely. The distance between Earth and Voyager 1 is 14 billion miles, 22.5 billion kilometers. It takes nearly an entire earthly day for the signals it sends back to us to travel back to Earth. In other words, Voyager 1 is approximately one light day away. It is truly amazing that this spacecraft, launched in 1977, is still operating outside our solar system and transmitting data. Ocker stated, "This research is scientifically significant. It is a tribute to the incredible Voyager spacecraft. It's the engineering gift that keeps on giving to science." But how does the solar system's boundary affect you? Outside of the bow shock, all of the high-energy cosmic rays are present. There is then a slight decrease in the number that make it to the heliopause. and more than half are halted between the heliopause and the termination shock, which is located at about 100 AU. This leaves less than 25% permeable to the inner solar system. The region where the solar wind slows down and interacts with the interstellar medium is known as the solar system boundary. There would be at least 4 times the amount of cosmic rays in the solar system if the solar system had no boundary, or if the boundary changed size so that it was inside the orbit of the Earth. Fortunately, the Earth's magnetosphere shields us from some of the cosmic rays that enter our solar system. However, if the number of cosmic rays entering the solar system increases dramatically, the amount of high-energy cosmic rays that can reach Earth's surface may change. The Earth's ozone layer may be damaged, and cosmic rays may cause DNA damage and mutation. Let's hear what impresses you most about the Voyager mission in the comments section below.